started, an RC circuit, the R and the C stand for step. They probably stand for resistor. There you go. So we're going to draw ourselves a little RC circuit. An RC circuit's going to have a capacitor, and it's going to have a resistor. Generally, there is some switch, okay? And then at some point in the story, we have to charge the capacitor. So often when you look at an RC circuit, like an actual RC circuit or an experimental design of an RC circuit, there will be a battery involved somewhere as well, okay? But the thing we really care about right now is just this. Does that make sense? And we're going to talk about RC circuits in kind of two cases. So a capacitor is a device for storing charge, kind of like a battery, right? Okay, but it's not going to continuously flow. We're only going to get one round, right? Because you've got all those positive charges hanging out here, negative charges. So the negative charges are going to go through one time, and so it's not going to last forever. It's going to last for a short amount of time. The length of time is what we're going to worry about today. That's what we really care about today, okay? But it's serving the same purpose as a battery would in that you're providing a potential difference. Okay? When you close that switch, then you're providing an electric field through that wire, and then you're going to have current flow. Does that make sense? Okay? So the two kind of cases that we care about one case when we are discharging the capacitor, and the other case would be when we are charging the capacitor. Your book does them in the order that I just said, so that's the order we're going to talk about them in. So let's talk about discharging a capacitor, shall we? All the enthusiasm that just happened there was amazing. I just have to say that. That's right. Thank you. Shumway is excited? Is that what you said? Yes. Awesome. I'm glad. All right. So we're going to go through the derivation here, not because it's something that I think you have to know. I think it's something that is kind of nice to see where it comes from. And it's pretty straightforward. What's up?
This is the thing with the funky E's of power or something.
It is an exponential, yes.
It's funky.
I don't know that I would call that funky. I mean, like we've seen.
An afro.
Whoa! Yes, it is an exponential. We'll see it in just a second. Is that fair? Okay. So at this point here, we're assuming, or we are setting this up so that we have a capacitor that is charged. Once I close the switch, I have a loop. Kirchhoff says that around any loop, what do you know about the potential difference?
Zero.
Has to add up to 0, right? So we can say that the potential difference across the capacitor plus the potential difference across the resistor must equal 0. We've got definitions for potential difference of a capacitor. We know it in terms of the charge held on the capacitor divided by the capacitance. And we know the voltage on the resistor, okay, based on the current and the resistance of the resistor. Does that make sense? But if those are going to add up to 0, then you know that one has to be positive and the other one's got to be negative. So I'm just going to set this one equal to, or set that one negative. It doesn't really matter which one, right? It's kind of an arbitrary decision, but we're just going to go like that. Okay. So the thing to know about this is that as soon as I close this switch, unlike a battery that's got a chemical process that is continuously causing that potential difference, as soon as I close that switch and charges start to move here, okay, this Q is changing. Does that make sense? There are only a finite number of charges. So this Q is changing. And as that happens, what else is changing? The current is changing. So the capacitance is constant, right? That's a constant for the story. And the resistance is constant. But Q and I are continuously changing. So it is a function of time. So if you look at this equation at any given time, Q and I are instantaneous values. It's supposed to say only, but it's hard to read. Okay. And I should have written in here that this is once the switch is closed. Just to be very clear about what's happening here. Now we can take some steps here and combine things to get the funky E thing that Nathan's so excited about. Okay, so we have to get there somehow. And the way that we're going to start that is by our definition of what current is. What is current?
The change in charge over time.
Charge per time, right? So dq dt. So the charge that's going through the wire divided by the time. Now, if there is charge that's moving through this wire, what do you know about the charge that's stored on these plates? It's changing by the same amount, right? As this thing goes up, this thing is going down. And so one way to say that is that the dq in the current is equal to negative d. I'm going to write that as a capital Q, where this is the charge on the capacitor. Okay. So instead of writing that as d little q like we had done, we can write this as I is equal to negative d big Q dt. And that's nice because then I can relate it to the big Q in that green equation there. Okay? So I can put these things together and say that Q over C, so I'm copying this from the green equation that's at the very top, Q over C plus R times dq dt has to equal 0. Because I could divide by an R. Okay. And then I've got kind of a cute little differential equation. Not one that's super hard to deal with. I'm just going to separate my variables, so I'm going to put the Q stuff on one side and the not Q stuff on the other side. Is that okay with everybody? So, what?
Didn't you say that the big Q is also changing?
It is.
Oh, no, that's a variable.
Yes, yes. Yeah. So the only two things that are constant here are the C and the R. Yeah, yeah. So I can write this then as, let's see, dq over Q, it's supposed to be a Q, there we go, is equal to negative dt over CR. Is that okay with everybody? So I'm just separating out my variables. So then I can do some integration to solve for Q as a function of t. Are we okay? Everybody happy enough?
Yeah.
Okay, okay. So I want to integrate both sides. And I want to talk about from the beginning, when I close that switch, to sometime later. Okay? It doesn't have to be at the very end, because really, when is the very end? But it's just going to be from the beginning to sometime later. So let's go ahead and integrate on both sides. On the Q side, we're going to start with whatever initial Q we have, Q naught, and get to some other value, Q. Okay? And on the T side, we're going to start from some time 0 to the time that we're actually talking about, T. So the amount of charge, this Q up here that's in the limits of integration right here, okay, that Q is the amount of charge that will be present on the capacitor at this time T. Everybody okay there? So let's do some integration because we can. So if we integrate the left-hand side, let's do that one first. 1 over Q dq is just going to be?
Natural log of the absolute value of Q.
Natural log of the absolute value of Q. So let's say ln of Q, that's going to be evaluated from Q naught to Q. And on the other side, the C and the R are what? What's that? Constant. I heard wah. I'm like, yes, they are wah. I don't even know what that means. They are constant. So they have a negative 1 over CR times time that's evaluated from 0 to T. Plus C. Well, I don't need a plus C because I have my limits, right?
They
Yeah.
cancel.
Right. Yeah. So it's okay. All right. So then if I apply things like my 0, that's going to go away. And then if I apply these two limits over here, I'm going to get something like the natural log of, that's going to be like Q over Q naught. Is that okay with everybody? Is equal to negative T over CR. But I want to solve that for Q. And so I say to Nathan, if I want to get that Q out, and it's being natural logged right now. Is that a verb? It is now. Yeah. Natural log. What am I going to do, Nathan? Do that funky eat. Says yes, just like that. Let's do that. I can't even say it with a straight face.
Do that funky eat.
It's just not okay. All right. Woo! All right. So when I do that, I can't.
Don't say it.
I can't. We can solve for Q. That Q naught is going to come over to this side if I want to get Q all by itself. Is that okay? E to the negative T.
That funky E.
Right.
You're not calling it by its proper name.
I refuse to. That is true. And this is an equation that you will see. I mean, this is a fairly traditional way to write this. Often, though, instead of writing C times R, we will call that its own little thing. That product, C times R. What's that?
Let's just call it RC so we can say RC resistors.
Let's not. We're going to call it
RC drive.
tau.
Ooh, called it. Because I didn't read the book.
Or anything like that, right? And that is the time constant. Not torque. No, in mechanics, yes.
More confusion and
Oh, life is hard, buddy. I'm sorry.
Yeah, too. Just to make it more confusing.
What's that?
Add a vector hat too.
No, it's not a vector.
The time is
What are the units here, friends?
second.
Seconds. I want you to prove that for me real quick. I want you to go through, think that through, show me on your paper, talk it through with your partners, prove to me that, bless you,
Let's see.
that the units of capacitance times resistance gives you time.
Second.
Go.
Sorry.
Okay, let me ask, where did you start?
I didn't. I don't know where.
Okay, so I want to look at the units of C and the units of R, and my claim to you is that if you mix that together and smash it together a bit, that you'll get seconds out. So how are you going to show that? This is like question number 27 from freshman year.
Multiply
Oh, yeah, this is not out.
units.
Okay, so what are the units of C? What is C? Let's back up. Capacitance. And capacitance is measured in what?
I didn't know.
Oh yeah, sure.
It's farads, yes.
Because an ohm.
And resistance is measured in ohms.
Coulomb per second.
Well, that doesn't look like a time, does it?
Multiply that by farad. And farad
Drat.
is coulomb per volt.
Okay, so that means we need to figure out more stuff. What is a farad?
Coulomb per volt. A farad is a coulomb per volt.
A farad is a coulomb per volt. Are you okay with that statement? If you're not, go back to what a coulomb or what capacitance is. Capacitance is Q over V, right? So that means that a farad must be a coulomb per volt. What is an ohm?
It's a volt,
volt
per amp. And an amp is a coulomb per second.
Yes.
Hold on, don't take too many steps at once. We're taking baby steps here, friend. All right, so resistance is voltage over current. Is that okay? So if we look at the units there, that's going to be a volt per amp. And there still isn't a time in there. Darn it. But we see volts go away, right? So let's get rid of them. Is that okay? So now we're left with coulombs per amp.
Amps is just coulombs per second.
Right, but an amp, that's current. And we know that current
Charge per time.
is dq dt, right? So that's really like coulombs per coulomb per second, which is seconds. Well, that's cute. So it is a time constant. That's really what it means. Okay? So I'm going to rewrite this equation just with the tau in it because I know that Brian's excited about writing that tau. So we're going to say that Q is equal to Q naught e to the negative t over tau. I'm going to put a box around that. I did notice I was just looking at the equation sheet, and none of the RC circuit's equations are on the equation sheet. I will tell you that, oh, did I mention that there are RC circuits on the exam fairly regularly? So you probably want to know that the funky E thing will probably be involved with some of the free response questions that you'll see today, the ones that Logan is going to do on Monday and turn in, apparently, and that you'll probably need in the future. I'm not saying you have to have this memorized, but I'm saying you need to be familiar with this idea. Okay? Not only do they like looking at that, we need actually, let's do one little quick thing here and just acknowledge that we know that voltage is proportional to charge. Okay? Oh, because of this thing?
Shouldn't you write Q for charge?
Oh, yeah, sorry. Yes. Voltage, I wrote C on here, I don't know why, because I was crazy. Voltage is proportional to charge because we've got that little guy there, right? Capacitance is the proportionality constant. So we can write this equation again just in terms of voltage. So we can say that the voltage across the capacitor, let me just say that carefully, the voltage across the capacitor at any given time is equal to the initial voltage times e to the negative t over tau as well. Okay. Again with the funky E thing. It just keeps showing up, right?
Yeah, so you started saying it.
I did. I looked at Nathan in particular because I thought he would appreciate it. But he didn't smile, so maybe he didn't appreciate it. So I guess I probably won't do it again.
Because he hasn't thought of a joke yet.
That's true. I guess it usually has to do with when he has a joke. True. Point taken. All right. I don't feel defeated.
Does that mean you can also do that same thing for current?
Mm-hmm.
Yeah.
Okay.
Yeah. So you can write this a bunch of different ways, right? Yeah.
Equals I naught e to the negative t
Yeah.
plus d q.
They also, besides just writing the crazy E equations, really, really like to graph this. May not surprise you. If we look at this graphically, let's go ahead and just do a graph of the charge on the capacitor per time, or as compared to time. What's that going to look like? Any ideas?
It's going to go down
It will go down.
like this.
It
It crosses
crosses
the Q axis.
Mm-hmm.
What's this?
So where does it start?
At
At Q naught.
At Q naught, right?
And then it decreases at a decreasing rate,
So something like
asymptotically.
there. Okay. Now, not only do they want you to look at that, but we're going to take it one step further and say, what about if we look at specific times? Like, for example, what about at the time when t equals tau? That made Gabe really happy, apparently. When t equals tau, E is going to be equal, or what's that thing going to be? Right, e to the negative first, right? And e to the negative first is something that's it's about 37%. Okay? So we can say that when t is equal to tau, Q is equal to Q naught, or let me say it like this, 0.37 Q naught. So we can identify where that is, and that's about here, and that's at tau. Okay? So that's about 0.37 Q naught. And then we could do another one. Another interesting place might be when t is equal to 2 tau.
13%.
Approximately, yeah. Q is equal to about 13% of Q naught. So again, then you can say right here, just so you can get some sense of what's going on. Okay. The graph will look the same regardless of the initial charge, right? It's going to be the same shape every single time. You're going to see that graph a lot. Just letting you know. You should look excited about that because it's going to be fun.
Woo! Ow.
Right. All right.
Woo!
Good work. Good work. Let's see. So we said that we could find Q, we can find voltage, we can also do I. It's all the same game. Okay? Same shape, same stuff. I heard that there were some people, and I don't know if it was you guys or if it was people that are in AB, must have been AB since it was Marchetti who came to ask me about it, that were getting picky about when you have an asymptote. And so, like, when is that capacitor fully discharged? Well, does it ever actually get fully discharged? No. But the book did point out, and so I'm going to tell you this, just kind of put it out there, that when T is about 5 tau, okay, then you're about 1% of the initial charge. So we're going to call that, like, pretty much done, okay? So knowing that it won't ever fully discharge, but acknowledging that the amount of charge on that capacitor is going to be pretty darn low. Does that make sense?
I'm pretty sure by this time we were.
I'm just saying.
With, like, asymptotes.
No, but it's less the asymptote and more the orneriness of making sure that you're answering the question they're asking. Do you know what I mean?
Yeah.
As opposed to just
So if on the AP test
being
they
a
ask-
snothead about it. I mean, let's be honest.
So if on the AP test they ask,
That'd be Matt's awesome.
like,
Yes.
when will the capacitor be discharged? Like, will they ever even ask?
I
Heard about it.
am not going to say yes or no because I have not looked through enough AP questions to say absolutely they'd never say that. I think if you ran into a question like that, you could say it will never fully discharge, but after about 5 tau, you're going to be at about about 1%. So that's pretty darn close to 0.
Okay.
I think that's a fair, good answer.
Okay.
Is that okay?
Yeah.
Okay. All right. Now you know everything there is to know about discharging a capacitor. Good show. All right. Let's charge a capacitor, shall we?
Oh no.
Yay!
Oh no, am I right? It's okay, you can laugh.
What?
It's okay, you can laugh.
No, I can't. I start coughing and that hurts.
Are you broken?
I think I'm sick.
Oh no.
I'm pretty sure I'm sick.
These are sad things.
Chairs now.
Bye.
All right. So the charging a capacitor process, like the discussion is going to be pretty darn short, mostly because we're not actually going to solve the differential equation because, well, I mean, you can, I just don't really want to. And it's beyond the scope of the course for what I need to do with you. So there you go. All right. In order to charge a capacitor, we need to have a battery or some sort of potential difference that's going to allow us to charge it. Okay. We're going to have a resistor in there to moderate the current. And our capacitor, okay? When we're charging our capacitor at maximum, delta V sub C, the potential difference across the capacitor, will equal the potential difference across the battery, or the EMF, okay? From that, we can also say that the maximum charge that we will have sitting on that capacitor will equal the capacitance times delta V sub C max. Because we've got a nice little loop there, we know that the potential difference across all 3 of those pieces have to add up to 0. Yay for Kirchhoff. We love him. What a good guy. So we can say that the potential difference of the battery, I don't know why in your book they keep switching between the epsilon and the V, but I'm going to just stay consistent with what they do so that if you go back to look, you can see it. Okay? Plus V for the resistor plus V for the capacitor has to equal 0. So let's make one of them negative or 2 of them negative. It doesn't really matter. Really what we want to say is that the battery is going to be equal to VR plus VC. We're going to take the same kind of game we played before. So VR is going to be equal to IR. And VC is going to be equal to Q over C. And I'm just going to call this V sub B for the battery. And when you look at this problem then, so I'm going to do the same thing with I that I did before. Instead of writing it as I'm going to write it as dq dt. Okay? Same, but it's not negative this time. Correct. It's not negative. So I'm going to write this as dq dt times R plus Q over C. So we've got a nice little differential equation again, right? Problem is that we've also got this VB over here that's not 0. So it's a little harder to solve. It's not quite as clean and beautiful. Okay? So my diff EQs people are like, oh, I could do that, and good for you if you can. I'm not going to worry about it right now. If you would like to go through it, you are very welcome to. I'm going to tell you that when you solve that, so you get 0 is equal to dq dt times R plus Q over C minus VB. Solving that differential equation. Really? Did you really die? Oh, no, there it is. It's coming back. That would have been really sad. It was like the very exciting moment. My computer apparently also does not want to solve a differential equation today. I don't know why. Slacker. It also has a strange, weird E thing in it. Doesn't look quite the same though. It's the capacitance times the voltage of the battery times the quantity 1 minus e to the negative t over r sub c. Brian says, but wait, Miss Carboling, I don't want to write r times c. I said r sub c, I meant to say r times c. I want to write what?
Tau.
Tau. And oh, by the way, this c times VB thing, that's also just the maximum Q. And then you're going to put a box around that one. So those two equations are the equations that we really care about. Those two equations are the things that you're going to see a lot of. Okay? So is this one going to be a negative curve? No, right? We're charging the capacitor. So it's going to go up. Does that make sense? All right. Yes. It's going to have an asymptote. We're not going to freak out about the fact that it's going to have an asymptote because we're mature enough for that. What questions do you have right now? Gabe, you look like you have a question.
Yeah. Why isn't it negative dq? Oh, no, yeah, right.
Because it's not pulling the charge off of the
this time it's
capacitor.
Charging it, yeah.
Yes.
That's right.
Yep. Other things? We okay? Oh, more.
Sorry,
Yeah.
one more. Why didn't we put deltas on these?
Because I was lazy.
Okay.
You should have. If you're a good kid, you would have.
Whoops.
I mean, it doesn't matter. It's kind of like having a delta t versus a t in a lot of ways, right? Like change in time. I mean, there are some reasons when you really care, but for our purposes, it doesn't really matter. Does that make sense?
Yeah.
You're not going to lose points on an exam whether or not you have the delta.
Okay.
I guarantee. All right. So let's do a lab to see this in action because it's kind of fun.